Okay, so now it's recorded, and this will be available. I'll post it on on YouTube, but it will be something that is not publicly available. So just there will be a link for people to see our discussions, our content. Now let's start with maybe. Yes, please, if you have a question. J.K. Liang. Do you have a question? Okay, no. All right. So let's continue then. Who has a question? Because we had almost like 3 lectures on Monday, and if you look through material that I was providing, it should be available on Quarkus, and also those who visited lecture. Do you guys have any questions? Also, there are lectures on the YouTube channel that you could see. We'll be more or less following the same list of topics, so you could even check lectures ahead of a time and see if something potentially not clear, you could ask questions. All right, someone asked whether that's gonna be tutorial or lecture, something in between. I guess we will do some material refresher on the complex variables, complex numbers, and functions, and we consider a few examples so that you are familiar. That's the plan for today, because as you've seen previously, the wave function that is the main object of quantum mechanics, it's generally a complex function, right? So of space and time. And so that's what the object that people are curious about in quantum mechanics, because that's the solution of time-dependent Schrödinger equation, and that's what we want to obtain, because that object gives access to properties. Any property you could think of in quantum mechanics, they could be obtained from the wave function, right? That's the idea. Okay, so in classical mechanics, you have trajectories of particles. You could have solid bodies that potentially also studied, but could be considered as particles, depending on your level of consideration. And then finding the trajectories from Newtonian equation gives you properties. So in quantum mechanics, we study properties through first finding the wave function and then getting the properties out of the wave function. That's the kind of general idea. Now, let's review a little bit of complex numbers. I'll share my screen. Okay. Oops. The right file, but I would like to share it differently. Just a second. Okay, great. Now you see my iPad. All right, so as I heard, you guys familiar with the complex variables, complex numbers. This originate from desire to take a square root of negative, right? This quantity I, imaginary unit, square root of -1. You square it, you get -1, something to remember. Geometrically, you could think of it if positive numbers are along this x-axis, and negative numbers is rotation by pi, right? Then the complex numbers are rotation by just half pi over 2, right? So, and then if you do this rotation twice, then you get to the negative naturally. That's one way to think about imaginary unit geometrically. So complex numbers are generally written as real plus imaginary part, and as we talked, the wave function can be written as a real plus imaginary part, right? Both of these functions are real because we have now I in front of imaginary part, and you can always find real part and imaginary part separately by taking psi, let's say. For the real part, you can do psi plus psi conjugated divided by 2. That will be psi real. Another way to write this quantity is real psi or real number. And imaginary part could be obtained by just doing the psi minus psi conjugate divided by 2i. Another way to say it's imaginary part of psi. Right, so this is for numbers, this is for the functions. And the complex conjugation is the operation that is doing this. You're just changing the number, the sign in front of the I component. If it's negative to positive, it's positive to negative, right? So that's what conjugation does. Now, with any numbers, you could, it's a, mathematically speaking, complex numbers form the field. What this means is that it means a certain things like you can add, subtract, multiply, divide, right? And you have 0 with respect to addition. You have also sort of identity with respect to multiplication. The only thing you cannot do with complex numbers, which you can do with real numbers, is compare them. Like you cannot say whether this is bigger than this or not, or the other way around, right? So because it's not defined procedure. Yeah, but other operations like addition and multiplication and the inverse of those, they are well defined. Any questions regarding this? Because this is a good time if you ask. Okay, so then, well, when you multiply, you need to account for the fact that I square is -1. So this is a simple example. It's 2 minus I. This is -3 plus 2i. If you need to multiply them, we go multiplying and then cross terms. Don't forget about them. I with 3 and 2i with 2. Right, so that's what you get. And if you have any uncertainty about this procedure, let me know. Or you could also review this. This is a relatively straightforward material that you can find anywhere, really, on the web, Wikipedia, what complex numbers operations are. Complex conjugation, as I was saying, very useful in quantum mechanics because, as you will see, let's say if we want some properties, very frequently what we'll be doing is, I'll talk about measurement more in details later, but very frequently we will be considering the integrals from, let's say, a to b, where a and b could be infinite or finite, right? And then even in the kind of some discussion about wave function and what it means, we had the integral like this with a psi xt with star. psi xt, right? And this quantity is known as absolute square, right? So it's absolute square, meaning that it's always positive or equal to 0, non-negative, mathematically speaking. And there is a simple kind of reasoning behind why this is positive, because, well, for any number like z, or like we could consider this example, for example, for concreteness, right? So if you have z with z star, or z star with z, they commute, meaning that, well, all multiplication of all numbers, you could do it in any order. It's commutative, as you will see in a moment. When we deal with operators, that's not the case, but with numbers it is. So then if we do this multiplication, then we're going to get positive number. While if we do z squared, that's not necessarily positive, right? So mind the difference between z times z star, absolute square, and the regular square, right? Let's do the absolute square first. So 2 times 2 gives you 4. Then 3i minus 3i gives you plus 9, right? Because I times minus I is 1. It's the extra minus. And then we have cross terms, which are complex, but they will cancel each other, as you see. 2 times 3i and the minus 2 times 3i, right? So they cancel each other. You get the positive number, which is 13. In contrast, if you do z square, in this case, you're going to get, well, something that is not necessarily positive. So let's see, you get 4 again, and then 3i times 3i is giving you minus 9, because I times I is minus 1. And then you have cross terms, which are essentially plus 12i, right? So you're going to get, technically, 4 minus I is 4 minus 9 is minus 5, right? Plus 12i. So that's the real component is not positive, and there is a complex component. So as you can see, the square of the complex number could be anything complex, right? And the absolute square is always positive, which is nice. Because it's nice because the physical meaning, then we could assign to the absolute square is a probability density, because any probability density must be positive. It cannot be negative. And this type of integrals we'll be dealing with. Also, we will be dealing with, as you will see, any property like kinetic energy, for example. Any property could be characterized by similar integrals dx, where the operator will act on the function, and then we will multiply that result by the conjugated version of the function. For those who study linear algebra, this can be considered as a like vector psi inner product with operator. Yeah, I guess in linear algebra we also introduce operators or matrices, and an inner product with a vector. So the conjugation is not written here because in linear algebra, things assume that in inner product in the complex space, you have a always conjugation. The way the inner product is usually defined is that it has a conjugation in this part that is in the quantum language usually called bra part, and this one is a ket part. And the reasons they're called like this because in the quantum mechanics usually the inner product is just written with this bra and ket notation, which is just another way to write the same thing. It's either with the round brackets or square or this angular brackets. What this means is pretty much this integral, where the limits are plus infinity here, the space essentially minus infinity here, the entire space. All right, but that's why this conjugation is important. It's appearing in any property. Okay, now this is essentially the stuff that we already have seen, just with another example. Z equals 3 minus 5i. That's Z's absolute square is positive 34, sorry, right? And and then that absolute square is not the same as square. Division of complex numbers is a little bit more challenging, but you can do it by simply, here's an example. The way we divide is we complete by adding it's not a completion of the square, but we essentially turn the denominator into the real number by multiplying with a complex conjugate. Just generally speaking, if we have z1 divided by z2, what we do is we multiply these both expressions by z star 2, and then we get the real number in denominator, and we know how to divide by real numbers, and the numerator is some complex number. And we've already seen how the complex numbers are multiplied. Okay, so the result you can check. Now, another thing is how you can visualize the complex numbers and the different representation of complex numbers, which is called polar representation. You could, since the complex number is just a point on the complex plane, you can characterize this point by xy coordinates, right? Or by the angle and the radius. And that's an alternative representation of complex number, like z equals to r e I phi, where you connect x equals r cosine phi and y equals r sine phi. Right, from this formula, you could derive what r is. It's essentially square root of x squared plus y squared, or absolute z number, right? And then you also can get phi is arctangent of y divided by x. Important formula related to, I guess, exponential function of a complex number, this I phi, it's like this. It can be written as cosine I sine. This can be checked by just comparing the Taylor series if you want. Or you could just remember that this is the formula for exponential function. Okay, of course, with the I phi argument. And then things that we will be doing in this course quite a bit is complex conjugation for this exponential function. Just a changing of I, sign again, right? And then that results in the change of the I sign in the resulting expression for the Euler's formula. You could also treat the more complex expressions with the real and imaginary part. So all that is relatively straightforward. But if you have any questions, let me know. Okay, so complex functions. We will be dealing with some of these complex functions, but usually they will be somewhat simplified in the sense that the functions will be of real values, real variables, right? Something like this, where x is real. It's just the function has a complex component, right? But the variable at least is real because, again, in our wave function, we have x and t. Those guys are real space and real time, not complex. So we therefore don't need like all like the entire complex calculus, which talks about usually functions of the complex variables. Our functions are complex, but the variables are real, right? So then things will be somewhat simpler in that case, because we won't have differentiation or integration over complex variables. We will have differentiation with respect to real variables and integration as well. So here's one example where you just differentiate sine as a sine function and make sure that you account for the fact that well, there's sometimes algebra with I that you need to do properly. So like in this case, you just differentiate with respect to theta, and ik is just a constant that comes out. And here as well, you differentiate, things come out the usual way. Nothing complicated. Okay, so if we want to conjugate functions, we do it the same way. We just change the sign with respect to I. Of I, really. Here's a simple example. Okay, and this is another example where you find I and change the sign when you do the conjugation. Okay. So there is nothing kind of difficult here. And that pretty much ends this refresher on the complex numbers. Do you have any questions? All right, so if there are no questions, let's consider another part, which will be about the wave function, its properties and interpretation. Somewhat a repetition of things that I already said earlier. I'm looking at the chat. Okay. I guess, as I said, you see, it's easier if you ask the questions kind of using your microphone. so that I could respond to them sooner. Now, earlier, the question is whether earlier rules is the definition or could be calculated. First of all, it should be calculated. And then someone already answered, could be proved, but I think we just remember it. Okay, so how do we prove Euler expression? Anyone like to pitch in? There will be extra points for attempt to say something smart. All right, so if there are no volunteers, the easy way I know is you just do the Taylor series expansion for the exponent. What is the Taylor series? Do you guys remember what Taylor series is? Okay, so I'll remind you, Taylor series is this infinite series for non-polynomial functions. What you do for general function of x, you can write this as a expansion at a different point, right? So which uses the derivatives. So every derivative is taken at the point that we're expanding. You have increasing coefficient here. And so on. So generally speaking, we have a sum over fn x0 divided by n factorial x minus x0, n, where n is from 0 to infinity, right? Now, there are functions which have finite Taylor series, not infinite. Who can tell me what these functions are? All right, they called polynomials. They have infinite, not infinite, but finite series, because do you know why polynomials have finite Taylor series? That's very simple, because if the polynomial has a degree, let's say x squared minus 1, that's a polynomial of the second degree, right? If you differentiate it more than 2 times, you get 0, right? Because when we differentiate d over dx x squared minus 1, first time will be 2x plus 0, and then twice will give us just 2, right? And 3 times will be 0. Okay, so using this Taylor series, you can write down the exponential function in terms of polynomial, what this will be, and the function could be expanded at x0 equals 0. It's a convenient point, because of course in this case it's theta, not x, but the point is convenient because exponent is 1, right? So, but you could do it in other points as well. So when you do it, you're gonna get I theta of increasing powers and so on. And then you can compare this with you can compare this with the cosine of theta and I sine of theta. So cosine starts with 1, theta squared divided by 2, and so on. Sine starts with I theta, because there is an extra I here, minus I theta 3 to the 6, and so on. And so this is nothing but, if you sum this series, you're going to get the same series as for I theta with exponent. And that shows that, okay, exponential of I theta can be written as a cosine I sine. Another way to maybe prove the same thing is that using the formula that a cosine, say, of theta is I theta plus minus I theta by 2, and sine theta is I theta minus exponent of minus I theta divided by 2I. But all this is sort of, they need to come from somewhere. And I like to think that probably Taylor series is the most fundamental way of connecting these functions, because after all, what is function? It's really this non-polynomial functions. These are just Taylor series. If they are nicely behaving, they are representable by their Taylor series. And that's what we mean by exponent or sine and cosine. And that's how they are calculated in your calculator, by just doing Taylor series, because calculator or computer ends up just multiplying and adding numbers, and Taylor series is sort of a perfect recipe for doing that and obtaining the expressions for these functions. Any questions? Okay, so now let's remind you about physical interpretation of the wave function. We talked already that it's probability density. Obtain this way here. The time part is gone, because you could think of it as if we don't talk about time, that means there's just for a particular fixed time. Okay, we're considering things. And so to simplify notation, we remove time from the function. But generally, time is always there. No way to escape time, even in quantum world. Right? So the probability, the one that we talked, where my particle is between, say, A and B, you can obtain it by taking this integral. And that's it. So then there is a probabilistic interpretation that Max Born suggested. And the probabilistic interpretation is that we define what's the probability of finding particle through the wave function. But it's not only probability of finding the particle itself, but we could get other properties like total energy, linear momentum, angular momentum, kinetic energy, probability of finding the particle near X. All those quantities and others could be obtained from the wave function. That's why it's so valuable. All right, but now sometimes you're given a function that is not normalized. What this means is that you have some solution for the differential equation. Let's say we talked that the equation that we are solving is Schrödinger equation, like this. Now, if you multiply your function by constant, right? So what's gonna happen? If you substitute psi by psi prime, which is alpha times psi. The question now, whether psi prime is a solution for the same differential equation as psi. Who knows the answer? Alpha is not 0, of course, some constant like 5. Well, the answer is yeah, it's gonna be the solution, because how simply you could put it and do the operations. Alpha from here, from the left hand side and the right hand side, will just cancel out, right? And you're gonna get well, left hand side equal to right hand side. Now the only problem with that is probably gonna be if we, as we talked, have a particular initial conditions. They usually set up in the way that we should know what this function is, right? Now, at some point, we will be looking at the time-independent Schrödinger equation, which will look like this: h psi equals e psi. And the function there will be just a function of the space, not time. Some simplified version. So in that case, again, there is no initial condition because it's a time-independent problem that we'll be discussing. And there, multiplying by a constant is not a problem at all, because again, the left-hand side and the right-hand side stays the same. Just multiply by constant, and you could just cancel that constant if you want. But the reason why this constant is more or less fixed for us is the physical interpretation that we would like if we obtain a solution for Schrödinger equation. It's a mathematical problem. It should have clear physical meaning, which is that it should represent probability density, right? So that condition will be violated if you start multiplying function by some constants. And therefore, we just generally know that for a single particle, this integral must be 1 because particle exists and it's somewhere. We just psi axis sort of showing us where the particle is. What's the probability of finding it in different areas. And in order to get the right physical wave function, if you are given some function, what usually is done is renormalization. So meaning that function is not normalized. Let's say this integral is not 1, it's some constant. And then you could easily fix that by taking the value of the integral and writing the new, like probably can even write more suggestively psi of n normalized x equals to the one that wasn't normalized, the one that was given this integral, the c, right? You can divide it by square root of c, this constant. And then the new function, if you put it in the integral like this, minus infinity to plus infinity, dx, that will give you 1. And that's easy to see. Here's the sort of derivation, right? So you could see that after calculation constant, just do some division by the square root of this constant, and then the new function will be given c over c, which is 1. All right, that's the process that you'll be doing quite a bit in the homeworks, just to get some practice of normalizing functions. Interestingly, not all functions are normalizable, and that simply means that not all functions can represent physical system. Some just functions, mathematical objects that you can use. Say linear combination of such functions can be used, but individually they are not normalizable. You need a bunch of them to represent physical system, because normalization can be only imposed on some linear combination of those functions. But all the physical wave functions, they must be normalizable. So that means this c constant that we obtain if we take this integral, it needs to this c constant needs to be less than infinity, right? Because you don't want to obtain here infinity over infinity or 0 over 0. So clearly this should be more than 0, but less than infinite. And it cannot be negative simply because, well, the function that we're integrating is absolute square, right? So, and we know that absolute square is positive, so that integral will be always, should be always positive. Any questions so far? Okay. Now there are other requirements for the function, and that sort of set of requirements is that the function needs to be, well, continuous. It needs to be kind of differentiable in most of the points. And defined in the points, right? Everywhere. Otherwise, they're just sort of, we don't know about the system there in those points, right? So these are some examples. Like if you discontinuous, you cannot differentiate things clearly. Take the jump is not possible usually. We need to have continuity. Also, function needs to be a single valued. That's another physical postulate. This is, for example, non-single valued function, because for some points of x, you have multiple values of function. And this is the example of the single valued function. Now, the physical motivation here is that there shouldn't be two different values of space where probability density is like different. Now, could anyone suggest a situation where things are not single valued, but probability density is single valued? Well, if you have a probability density which is psi of x absolute square, and the function itself is psi of x, can you have a situation where this is a single valued, this is not single valued? All right, I'll leave this as a homework. It'll be fun to consider. Okay, so the third condition, wave function should be continuous most of the time, so we can differentiate. Continuity, of course, doesn't really sometimes give us differentiation. Continuous functions, continuous condition is necessary but not sufficient for differentiation. And in physical systems, there are situations like, say, on the nucleus, function not necessarily differentiable. So it is allowed to have some points, special points where function is not differentiable, but those are just a few points that cannot be non-differentiable in the continuous in some domain, continuous domain of x coordinate, spatial coordinate. And the functions that have properties 1, 3, which is single valued, differentiable, and continuous, right? So that's usually called well-behaved functions for most of the systems. We will be considering functions are well-behaved. Okay. And also we would like normalizable functions to represent physical systems, so that we could yeah, make sure that this absolute square integral is a constant, which is below the lower than infinite, so that we can divide by it, right? And usually for that, what you need is a function molecule is or any quantum systems that non-extended. It's usually finite in space, and space is infinite. So in order to have this condition, functions usually should decay to 0 at a large value of spatial coordinates. So functions like this are fine, like this are fine, because you see it's like decaying at the tails. But functions which are growing, they're not fine, because then you get the divergence of the integral. And here are some examples. I guess I will kind of hide the answers, and you could, considering that we're kind of running out of time a little bit, you could do it at home. How do you do this type of exercise? Well, you check whether, like, the exercises, which of the following functions are acceptable as wave functions. And this is something that we'll be doing homeworks and exams. You could sort of, well, check whether the conditions 1 to 4 are satisfied. And for example, in this case, sine of x, you could see that it will look like something like this between 0 and 2 pi, right? And then you have these functions represented as sine function between 0 and 2 pi, and then outside of that range, it's like 0. So the function is continuous, it's differentiable in all the points, but these two, which is fine, just finite number of points that are not different, where function is not differentiable. Then what else we have? We need to have a single valued function. It is single valued function. And the question also could be about the normalization. We could integrate function, its absolute square, right? And clearly, since it's a 0 outside of the range, this integral boils down to integral from 0 to 2 pi. Sine function is a real function, so we can just sine x dx, right? And we could take the integral. Now, even without doing the math, which you can do, I believe, you could see that the square of this function will be something that looks like this, 2 humps, because you multiply, you kind of square it, right? So from 0 to 2 pi, the 2 humps, and they have a finite area under the curve. So that is clearly less than infinity, right? So this finite integral. So that function is physically acceptable, okay? And then you could, I'll post this, you could check the others and check here the answers. You could check that you got them right. Try to do that first and then look at the answers. And some of the questions like that will be in homework as well, so that we could see that you understood the material properly. So we now at the end of the hour. If you have any questions, I'll be happy to answer. If not, then we can stop here.